Hey there, welcome to a video discussing section 6.2, which is on sigma notation. So you'll see this Greek alphabet right here, which we call sigma, and something called Riemann sums, which we're going to talk about in a few minutes. The definite integral we're going to spend more time talking about in class the next time we meet, and that's kind of the big part of spring semester calculus. We've done a lot of derivative work. Now we're going to talk about antiderivatives or integration. So the second semester is called integral calculus because that's what we do. So first, a recap of sigma notation that you may have seen in pre-calculus, but I'm not 100% sure because I know we had a pandemic and we may have cut some things out. But what this means, it means to replace and add. That's what it means, replace and add. So for example, this is your formula. It's A with a subscript, K in the subscript. K equals 1 is how you start. And the 5 up above is how you end. The way this works is you simply write A1 plus A2 plus A3 plus A4 plus A5. And that's it. Sometimes we call the K value here the index of summation. So what you're doing when you do sigma notation is that you're adding up all the terms in which you're replacing K with. So you replace K with 1, then 2, then 3, then 4, then 5. So you kind of just go in order. And we call K the index of summation. And it could be really any letter. For the index of summation. So it's kind of up to you, whatever letter. You can use the K, you can use X. And there's a way you can actually locate this in the calculator. If you go to alpha, I believe window, I have my calculator right here. The alpha window, option 2. You can locate it, and then you can actually put like X. It'll kind of like show up like this. And I think if I do that, yeah, there'll be like a blank equals blank. There'll be a blank up here, and then of course, you got to plug in a formula, right there. So it's kind of up to you what you want to do for this variable. And usually use X if you're doing the calculator, or K, whatever. Doesn't matter. So let's look at this one here. How would this look? Well, you start with 1s. You do 2 to the 1 plus 1 power, plus 2 to the 2 plus 1 power, plus 2 to the 3 plus 1 power, plus 2 to the 4 plus 1 power. And you add them up. So you get 4 plus 8 plus 16 plus 32. You get 60, I believe. Yeah, something like that. And here, if you see a K equals 1, here I did J, here I did K. Same thing. Doesn't matter. Use any letter you want. Now, this one's kind of crazy. This is going from 1 to 20. So, and there's a J also being multiplied. So it's 1 times 2 to the 1 minus 1 power, plus 2 times 2 to the 2 minus 1 power, plus 3 times 2 to the 3 minus 1 power, plus dot, dot, dot. And then we go to the last number, 20 times 2 to the 20 minus 1 power. I don't expect you to actually know how to add all that in your head, but just so you know how it looks, like the pattern. There's supposed to be a time sign. I don't know what happened. There's a formatting issue. So this is what we're going to be working our way towards. We're going to be working at this formula mainly. So here you have n, here you have k equals 1. So you start with f of c1 times delta x sub 1. Then you do plus f of c2 times delta x sub 2. And you keep going until you get to the last term. And we don't know what it is because you have n here. So we'll call it c sub n times delta x sub n. Now, let's look at example 4. Suppose you had an LRAM area where you had your delta x, which is 0.5, right? And you have 0.5, 0.5, 0.5, and you have f of x1, f of x2, f of x3, f of x4. And you can factor out the 0.5 to do it like this. To write this in sigma notation would be way more efficient. So you would just say f of x sub k, or any letter you want for the subscript. Start with k equals 1, and we go up to 4. So why do you use this? Really for efficiency purposes. It's more efficient to write it that way, and it's more compact and neat and nice. Plus, if you have like a fancy calculator or a computer program that can do this kind of addition, it usually would expect you to type it in this fashion. So and obviously I'm focusing on the summation of those 4 terms. That's why I go from 1 to 4. It starts at 1, goes to 4, and f of x sub k is my formula. Now, this is bringing us to a new topic called Riemann sums. So LRAM, RM, MRAM, we did it in the last section. We calculated some of our areas. Those are examples of Riemann sums. Well, what is exactly a Riemann sum? A Riemann sum is essentially a method used to approximate area between a curve and the x-axis using rectangles. So it's kind of what we've done already. In fact, you've been using Riemann sums, but the way you construct the rectangles could vary. So it's a matter of how you're constructing your approximation. So it's a method used to approximate area between a curve and x-axis using rectangles. So LRAM, RM, MRAM are all examples of Riemann sums, and they're just different ways of constructing those rectangles. And of course, like we had an LRAM area. So a Riemann sum essentially involves these 2 things: the width of a rectangle times the height of each rectangle. And you sum all them up. So you have a bunch of rectangles that you're finding the areas of, you're summing them up. Now, Riemann sums is very general. It's a very general kind of categorization for finding the area. So they don't have to be as rigidly constructed as they were in the last section. Actually, that should say, yeah, that's right. That should say 5.1. No, it should say 6.1. That's a typo. That's from the previous edition. For example, you could have, every rectangle could have different widths. You don't have to have equal widths. The heights don't have to be a left or right y value. We just had a rigid way of looking at it to simplify things in section 6.1. But they don't have to, again, be touched the left corner. It's always be touching the curve or the right corner or the midpoint. You really could draw them any way you like. And your function could either be below or above the x-axis. Again, we kept them above the x-axis in the last section because it just made things easier. But we do have to look at times when curves go below the x-axis, meaning the y values are negative. So the key idea, and let me do this as a text box, is that a Riemann sum is, and I do ask this in the Google form to answer you in words. Feel free to use some variation of what I'm about to type. Is sum of products of the form width of rectangle times the y value in that subinterval. Because you're going to have a bunch of intervals within an interval, so we call them subintervals. And let me expand that. There you go. So the sum of products of the following form: the width of a rectangle times the y value in that subinterval. That's a Riemann sum. So let's move on to page 2. Let's say we got this curve, so very funky. It's going from 2 to 10. Obviously, a portion of it is above the x-axis, a portion is below the x-axis. And it's closed interval from 2, again, 2 to 10, I already said that, sorry. And you want to make a partition for subintervals. So you have an interval from 2 to 10, but then you have the subintervals, intervals within the interval, right? And the widths are going to vary. You have a width of 2, a width of 3, and a width of 1, a width of 2. And we're going to create both heights equal to any y value. We're going to use any y value on the subinterval. So this will be my first interval, the width of 2. Next one, the width of 3. Next one, the width of 1. And the last one, the width of 2. And you can really draw this however you like. Like maybe I'll do that as one rectangle. Let me draw it again. So it's a little more straight. Notice I didn't quite do a midpoint. I didn't do a right-left corner. I did like a 3/4 point, if that makes sense. Here, again, I have kind of like total freedom how I want to draw that one. Here, I could probably do something like this. And then here, that's going to be a little tricky. But I have to connect. Well, I don't know. It's up to you how you want to draw it. I mean, there we go. So that's kind of what I just did. So if I take a look at it, obviously my first width is 2. And I made the height about 4.5. For the second rectangle, the width is 3. And I think I did the height at 1. For next one, I did the width of 1. And because I went down to -1, I'll put -1 there for the y value. And then here, I have a width of 2. And probably, I don't know, say 0.75, say. So again, you have kind of total freedom how you want to do this. So I got like 9 plus 3 plus -1 plus 1.5. So all that adds up to, I think, 12.5. So, you know, that's what we're doing. So will the sum be the same if we partition it differently? Like if I decide to do different widths or different y values? No, probably not. Probably might get something close, but it probably won't get the same area. Will the sum be the same if we pick different lengths or different heights in the interval? Probably not. You pick different heights? No. Now, but here's what we do expect as something to be a standard. Now, what would happen if for a function like this, we added the condition that we take the limit as the width of the widest subinterval approaches 0? Now, that's kind of weird. And I'm going to have to spend more time talking about this guys in class again, but we took the widest subinterval, which obviously is this one right here, and had that approach 0. So if the widest subinterval is approaching 0, then all other intervals are approaching 0. Or all other subintervals. Let me be more proper for my language, because it's an interval within an interval that we're dealing with. Remember, interval, the whole interval we're dealing with is 2 to 10. We're dealing with intervals within 2 to 10. Then all other subintervals will also approach 0, approach a width of 0. Like, for example, if the widest one's getting like 0.5, then the other one's going to be less than 0.5 because you want that to be the widest one. And what's going to happen to the numbers? How many subintervals will I have then? Infinite. You'll have an infinite amount of subintervals. Like, so if I were to erase all this right now and say, okay, I'm going to draw an interval. You know, this interval is going to be like super skinny, but I want that to be the widest one. Then I have a whole bunch of other ones that are even skinnier all the way through. I'm going to have a whole bunch of intervals, you know, that I'm drawing. And the thing is that the more intervals you have, more intervals, you get a more accurate area. So that's kind of the theory that's gone into this. And I'm going to kind of end it with this next point, because the next part's going to get really kind of messy with the notation. And I think it's best I do that live in person with you guys. The key idea is if you can find that limit. So basically what you're trying to do is you're trying to take the limit as the width of the widest interval approaches 0. If you could take that limit, then what you're going to get, I'll type this up here, is a fixed finite number for the area between the curve and the x-axis. and probably won't be 12.5. So I just did up above. And let me select that. Oops, select. There we go. And no matter, it won't matter how we partition, because we're letting each interval get really tiny, really narrow, really thin. Won't matter how many partitions we do, because we're assuming we're doing an infinite amount of partitions, or how we choose the y value for each subinterval. And so this is going to lead us to something called the definite integral, which I'm going to share with you guys when we meet again as a class. But before I talk about definite integral, I do need to do a little more theory. And I think it's best to do that in person with you guys, because it is a little wacky and it's not to do in the video. So we'll spend a lot of time with some theory stuff in class. And then I'm going to talk about what the actual definite integral is, and then do some examples with you guys on that. And it's going to be a lot of area that we're working with. So we've got a pretty intense lesson coming up. So buckle up. But at least for now, I kind of get you thinking about this, and that's what I care about. Okay, we'll answer the Google form, do the textbook problems, and you'll have your homework. I'll see you guys in class again tomorrow.